about some connections between the two subjects, which I hope you may find interesting. And essentially, I've broken this talk into two parts. The first part is an account of some work done on the optical properties of pneumatics with a former research student, then a colleague at Queen's. Well, he had a junior research fellowship at Queen's, now after Alberta, Claude Warnick, and it relates to the chiral phase or the helical phase of chiral pneumatics, and I'm basically trying to convince you that the optics of this medium, which is rich, is identical to the optics in a curved space manifold, which technically can be thought of as a group manifold. I'll try to explain what these terms mean as we go along. So that paper, to my surprise, was accepted by Physical Review E, my only Physical Review E paper. In part two, I'm going to be rather more ambitious and describe largely unpublished work. I've spoken about this at conferences, which relates the geometry of pneumatics to Lorentzian metrics in 2+1 space-time dimensions. So we can always imagine a space-time for which we suppress one of the three spatial dimensions. That's a rich subject, and I want to relate some rather exotic features of gravity, which are called gravitational kinks, to what I expect will be very familiar to you, the classification of topological defects in pneumatics. And as a spin-off, one gets a description of surfaces of pneumatics in a certain approximation as null hypersurfaces in this space-time. These topics don't exhaust the possible applications of relativistic ideas to liquid crystal physics. If one looks at smectics, as has Randy Camion and his associates, he spoke here earlier about this, then there is also the possibility of applying space-time ideas to their configurations, which he has done with great effect. What's the motivation? Well, there are two parts. If you learn a subject and teach it, it has certain techniques, ideas, and perspectives, and you would hope, and indeed it happens, that you can transfer this intuition to perhaps other areas of physics. When I embarked on my career in theoretical physics, courses in general relativity were rare in physics departments. I studied physics as an undergraduate, and they were confined to sleazy rooms inside maths departments. There weren't many contacts between physics and general relativity at that time. I'm speaking of the late 60s even, but they have by now become so commonplace that virtually every physics department offers a course in the third year in general relativity. So they've had to learn some of the technology, and it's the technology which can be transferred to perhaps other contexts, whereas years ago it would have appeared to be rather arcane and perhaps not worth the effort of learning the language. Okay, now general relativity is, of course, par excellence the theory of curved space and curved time, and its consistent description together with that of optics, light propagating in that medium. It's very difficult, of course, to engineer in the laboratory large amounts of curvature because you need very heavy bodies. And so some of the more exotic manifestations of general relativity are really beyond laboratory access. On the other hand, if one can find analogues in systems which can be manipulated in the laboratory, then that may have pedagogic value, may also teach us whether or not the various effects that we have in mind are really well-founded. And there has grown up in the community quite a large group of people who are interested in analog gravity, situations where what we have found theoretically could be perhaps mimicked in the laboratory. The most famous and the aim of much of this work is to find some sort of laboratory analog of a black hole, and even perhaps a laboratory analog of a radiating black hole, i.e. a quantum mechanical black hole. Well, that's part of the basic backdrop of what people are interested in. They, of course, would want to apply these to many areas of physics. Liquid crystals is just one possibility. So that's the general backdrop in which this, or the general area in which this work, I hope, should be viewed. Why choose liquid crystals? Well, you all know that there's a rich structure of topological phenomenon, particularly in the case of pneumatics, though not exclusively. And as I hope to indicate, there's intriguing connections with topological ideas in Lorentzian geometry. Okay, well, for me, a chiral pneumatic will be something for which there's an order parameter, the director, a unit vector, such that n dot n is 1, and n is usually equivalent to minus n. In other words, it's a direction field without an arrow on it, though in some circumstances it may have an arrow. And as I'm sure everyone in the room knows, these can in principle be birefringent, and the configurations they want to adopt, are typically those by minimizing a free energy, and you will get some non-trivial configurations. Now, what Warnick and I found is that if we take the helical phase, which I'll describe in more detail, it has the same optical properties as a certain three-dimensional, spatially homogeneous, but anisotropic curved space, which had previously been studied by general relativists under the name of a Bianchi 7 sub-zero universe. I'll explain what that means. But it's basically a curved space, and as a model, in fact, for the various anisotropies in the various possible anisotropies in the expansion of our universe. Here is a typical map of the CMB. This is a map of temperature over the sky, of the cosmic background radiation. We usually model that in terms of a perfectly round or homogeneous and isotropic space. But if you want to investigate what would be the properties if space were anisotropic but nevertheless still homogeneous, then you can, and that has been done. And what we found is a sort of model in which this actually happens, using the techniques that have been developed over the years to deal with these universes. Okay, so in principle, therefore, we expect to be able to, and we did, model an analog universe, an anisotropic generalization, if you like, of Clark Maxwell's well-known fisheye lens, which is in fact a model of a closed spherical universe. If you take the fisheye lens, which has the property that every point focuses to another point, not the same point all the time, then you can write down a refractive index for that, and in fact you're just looking, as I'll explain in perhaps more detail shortly, you're just looking at, in effect, light rays moving in a closed spherical universe. So what I'm going to do in part one is introduce in as simple a fashion as possible these underlying geometrical ideas. Key will be the idea of symmetries, and this will lead me to tangle a little bit with Lie groups and Bianchi's classification of three-dimensional Lie groups. Then I'm going to recall some basic properties of chiral pneumatics, and there's a metric associated with the chiral pneumatic, which I at least found in the papers of Jouet and Rubota, which is basically biaxial, well, I call biaxial anyhow. Maybe one should call them uniaxial, but it's basically the metric which will happen if you have a medium where there's a preferred direction but rotational symmetry around that preferred direction. And I'll try to put these two together. So that's part one. I'll tell you what part two is supposed to be when we get to it. So our story begins with Lobachevsky and Bolyai and the invention of non-Euclidean geometry, which we drop Euclid's fifth postulate. I've written it out here, but it doesn't much matter what that postulate is, but basically it's that if you take a straight, what you think of as a straight line and another straight line, then there's always a straight line which never meets it, and it's unique. Okay, so that used to be an axiom of physics, but it was found by these people that it's certainly not. It's an independent assumption of Euclidean geometry, and in the 19th century it was, of course, realized that it really was a matter of experiment or observation what the geometry of space is. You can't a priori decide what it is. Now, Helmholtz took hold of this idea, the being the universal man, and he classified all geometries allowed given the following assumption of free mobility. He said geometries are measured by rulers, and so let's try to find out what kind of geometries you could measure if you had a rigid ruler. So that gives you a notion of length. You want to be able to transport your ruler about so it's homogeneous. And the other assumption he made is that you can rotate the ruler about any given point. And you basically come up with these three possibilities. Flat space, which we've been familiar with for many millennia, and then Lobachevsky space, which has negative curvature, and spherical space, which has positive curvature. Perhaps spherical space is the easiest to appreciate because instead of having a sphere which you can embed in 3 dimensions, you just imagine embedding a sphere in 4 dimensions, and then the surface of that sphere would give you your spherical space. So straight lines in these geometries are geodesics. That's curves which extremize length, and therefore there is some measure of length, and the measure of length is coded into this optical path length, which, of course, if it were a physical medium, would be the refractive index. This is the square of the length interval times the physical distance. And in simple cases, well, here's the physical distance, the standard Euclidean distance, and then we'd have a refractive index. Now, to obtain these 3 geometries using a refractive index, we have to choose it to be like this, where k is the k on the previous overhead. So if k is 0, we're back to square 1, the optics of Newton. But if k is plus 1, then we get the sphere, and if k is minus 1, we get what's called Lobachevsky space. In fact, this is, if k equals plus 1, precisely Maxwell's fisheye lens. In other words, it's a medium, if you could make it, of course that's the issue, for which a bundle of rays here will focus onto another point here. Of course, if you move this point, you get a different focus. And this is not very difficult to understand because, of course, if you reduce by 1 dimension, then you will find that you're talking about the sphere, and it's quite obvious that if you start from 1 point on the sphere, the geodesics focus on the antipolar point. Okay, well that's the sort of history. Now, this is a very symmetrical setup. Okay, I just mentioned here Fermat's principle, which I'm taking as read. This says that Maxwell's fisheye lens comes this way. These are actually practical. There's something called a Lüneburg lens, which is used to look at over the horizon sources. It's something which is focuses radio waves or radar to a point. You can buy them on the internet if you type in Lüneburg lens, and you can get them from Amazon. They come next day. So that's a clear analog of a closed universe. Now, if we had a locally anisotropic universe, we wouldn't just have that scalar prefactor, we'd have a tensor, which we call the metric. And this corresponds to Riemann's generalization of of Riemannian geometry. And this is used, of course, essentially in general relativity. The difference between this and general relativity is that these indices are running at 1, 2, 3, and we're not doing anything fancy with time. Although we could just add time in as a kind of passenger, if we like, and then we'd have a 4-dimensional space-time metric. But the only interesting point would be, so far, the geometry of the spatial sections. Our universe is probably spatially flat, much to the disappointment of many people, because we can observe the expansion of the universe, and from the expansion of the universe, we deduce the spatial geometry. To lowest order, it could have been either of those 3 possibilities, but now we know 2,000 and so years after that that Euclid was actually right. It's as flat as a pancake. So it gives up anisotropy. There's every point privileged directions, as in a crystal, and but it is possible to maintain homogeneity. So you can have media which is fairly clear if you think of the optical analog, which are in some sense translation invariant, but anisotropic. The translations in these two cases, of course, are not necessarily going to commute. If you have two rotations, they don't commute, they give you another rotation. There are 6 possible transformations on a 3-sphere or on hyperbolic space. 3 of those are just regular rotations, but the others should be thought of as translations, and the translations do not commute. If they did, we'd be back to the flat case. So what we usually demand is that the composition of 2 translations gives another translation or generalized translation. You've got to be a bit careful about this S3, but it's certainly a composition of a group transformation. And these translations we are going to demand form a 3-parameter group, and this is what is known as a 3-dimensional Lie group. Now these groups were invented and studied, as the name suggests, by Lie and by Killing, and their aim in fact was to strengthen this idea of Helmholtz to discuss what kind of congruence geometries you would have. Now obviously if it's anisotropic, it's not a congruence geometry in the classical case. You can't take a triangle and rotate it, but you can translate your triangle. And it was eventually Bianchi who classified these possibilities. There are 9 of them, and these methods are now absolutely standard in general relativity, which gets me to my opening remarks. And I guess this is Lie, this is Killing, and this is Bianchi, for those who know what these guys look like. Okay. Well, now I want to get back to some familiar ground. The energy that you minimize, you could take to be this Franco-Scene energy for a chiral nematic. So this is fixing, should be a square here, should be fixing the length, at least up to, and it's a Lagrange multiplier for the length. And this is the derivative. Now the derivative is the ordinary derivative plus this extra bit, which takes into account twist. And I want to interpret that in a certain way, which I'll come to shortly. Now the bulk term would be minimized if that was 0 or small, in fact 0, but that's not possible because this system, as is well known, is frustrated. If this derivative hitting on n were to vanish, you can take a commutator and get a contradiction. So it's a frustrated system in the language of statistical physics, and so it adopts a compromise, and the compromise I want to talk about is the helical phase, which is, I'm sure, familiar to everyone here. The director just wanders around with a certain pitch length, and is constant. It depends only on the z direction. That's the assumption I'm going to make about the helical phase. Just a few remarks here. This does actually bring us to general relativity. This is an old story and not my own. This derivative acting on a vector field is known to relativists as a metric preserving covariant derivative, which has torsion. This is the usual flat connection or derivative, so you can parallelly transport vectors with it by assuming that the derivative acting on a vector is 0. And this bit is part of what's in the literature called an affine connection, which is antisymmetric on its indices, in fact all of them, and so it's pure torsion, as we say. The bit of the connection that is antisymmetric is called torsion, and it preserves the metric. So if I have a direction, I go along a direction like this, I have a vector like this, I just rotate around as I move along. That's what parallel transport means. This was used by Einstein and others and still arises in modern theories of gravity, for example, supergravity. And the failure of these operators to commute is what we call curvature. So that's a sort of side remark. This may be familiar to people because famously on the three-sphere, I mean, there are constructions of this connection due to these authors, Wright, Mermin, and Sethner. This is Sethner, this is Mermin. I couldn't find Wright's photograph. If you actually lift the system to S3, they showed that in fact you could get rid of this curvature, and that was their way of removing frustration in what's called the blue phase. That's a beautiful story, and in fact it's one of the reasons I got interested in this in the 80s, reading about that, because it was basically sheer general relativity all the way. It's a beautiful paper, and I'm sure some people are at least familiar with it in this room. Okay, well, the liquid crystal is here. This is a typical thing seen through cross-polarizers, and I guess everyone knows what these dark spots are, and so I won't labor this point here. Here are defects, and in fact that's another connection between liquid crystals and general relativity, but a slightly different one from what I am wanting to talk about. These line defects correspond in cosmology to cosmic strings, and there's been a lot of activity in which people try to simulate phase transitions in which cosmic strings might have been created by considering liquid crystals. So that was an activity some years ago. It's less popular now because not many of us are so convinced by the existence of cosmic strings, but there you go. Now, the main point of this talk is that the helical phase is clearly invariant under translation sideways and a screw rotation. And the important point about that is that by means of a translation and a screw rotation, you can get to everywhere in this room. I just have to move here and then move up there. And by adjusting it, I can get to any point that I wish. That means, in the technical term, that there is a simply transitive action of this group on the space of this room. Actually, I'd go out of the ceiling, I mean, if I had a big enough thing. So that means that I can identify this room with a group manifold, the set of group elements which get me from A to B. Okay? It's a subgroup of the full Euclidean group. It's, in fact, the universal cover of the two-dimensional Euclidean group. What I'm basically saying is the two-dimensional Euclidean group is acting, let's say, on this platform here. And of course, that means that when I do the rotation, I get back to myself after 2 pi. But if I, at the same time, do a translation up this direction, I never get back to myself, so I have to undo that 2 pi. So that's the group manifold, and if you look it up, this is a group of type 70 in Bianchi's list. It's one of the simplest groups that you can deal with, and of course people are very fond of it because the calculations are simple. Okay, so the phase of the chiral, this helical phase, I can think of in terms of this group manifold. Sometimes you like to think of a group manifold as a bunch of matrices. If I define this set of matrices, then I multiply them, they are again of the same form, and these get me around the group. So I can regard a group manifold, if I like, as a matrix space. That's another way of saying it. And I could write down the commutation relations, but I won't do that for a while. Now, according to these gentlemen, and to be frank, I don't know how popular this viewpoint is, but this is what I've read, is that you can introduce 2 refractive indices in such a medium. One is the ordinary ray and one is the extraordinary ray. They have a refractive index, and Fermat's principle then becomes this variational principle. This is the principle of least time given this formula. Now, in my language, this means that I square this and I get the optical metric of this medium. Okay? Obviously, if the extraordinary is equal to the ordinary, everything's boring. This term goes. I get back to the standard Fermat's principle. But if this is not equal to this, I have an anisotropic medium, and I have a genuinely curved metric. I can turn the handle of general relativity and discuss it. Now, it's clear that this metric is invariant by construction because it's only constructed from the director field under this group. So we have an invariant metric. The isometry group or symmetry group of our metric is given by this. Now I want to indulge in a little bit of technology. If this is unfamiliar or unwelcome to you, we'll go back and do simpler things later, but this is where we begin now to turn the handle. It's very convenient in this game to introduce these combination of coordinate differentials. These are technical one forms, if you like. They're not necessarily exact because if I take the d of, for example, lambda 1, it turns out to be the cross product or wedge product of the other of these two elements here. Now, this is a fancy way of building in the commutation relations of the group. One way to say it is that if I consider a vector field, which in place of this d by dx is something like d by dy, take the brackets, and then they give me the structure constants of my group. And so you see the structure constants of this group don't have much to say for themselves. They've only got these terms here. So it's a less complicated group than the rotation group. If you like, you can think of it as a limit of the rotation group in which we scaled out certain commutators. Well, now you see these are the squares of increments in dx and dy. Sorry, these are proportionate increments in dx and dy. And if you just substitute in, you'll find that these guys, this is the metric, but it's a more convenient form for the metric as it turns out. It's the square of these so-called invariant one forms. And part of the machinery of Lie groups is to say that these one forms are invariant under the group action. They are left invariant one forms, which means that every calculation we carry out will automatically build in the symmetry of these things. In fact, if, as I said earlier, if n equals NO, then we get the flat Euclidean metric expressed in a slightly unusual form. Now, I've used this d here, and this d is what's called the exterior derivative, or generalized curl. In fact, this formula is really curl of one of these is equal to the cross product of the other two, if you want to translate it into more standard notation. Or if you write it out, the derivative in the I direction of this guy minus the derivative. I'm sorry, there's some kind of typo here. There should be upstairs 1, but it's gone askew. So actually, this is what's used in the subject and also for electromagnetism nowadays in many books. It's called Cartan's exterior calculus. So this illustrates my point that this can be useful. Okay. Well, now we can start to try and use this machinery, and I'll just talk about some of the results which are in our paper. No doubt many of these results have been obtained by different means in the past. We're not claiming to have reinvented the wheel, or rather we're saying that this is a different description of how you might invent the wheel using this technique. And it would generalize, of course. So there are various levels that we could investigate light in this medium. One is ray theory, which I've really been talking about earlier. Another would be scalar wave theory, so I ignore the polarization. And then finally, I should really try to solve Maxwell's equations in this situation. And we went through all of these three with increasing complication. In all these cases, we can make progress because of the high degree of symmetry. That's perhaps not unexpected, even without knowing this machinery. As far as the ray theory is concerned, we can use Noether's theorem in a straightforward way to obtain constants of the motion and then get the rays. We have sufficient constants of the motion to separate variables in the standard way of mathematical physics, and that's what one can do. In fact, we can also easily handle the complexity of Maxwell's equations using these differential forms, which, as I mentioned, is an extension of vector calculus developed by Cartan. So, for example, we can use the two commuting translations to immediately write down constants of the motion which commute, and then we can reduce the whole thing to this set of ODEs here, and what enters are, of course, the ratios of these refractive indices, assumed constant, the momentum vector, and eventually we reduce the problem. Well, this is effective degree of freedom, which is z minus the theta coordinate, where this theta is just a theta determined by the direction the rays are going in. You can reduce it to this pendulum equation. For some reason, this is called in the books I looked up the quadrantal pendulum equation, but it's just a pendulum equation with a certain constant of motion chosen. Now, this has two different types of dependence, as you would expect. So here are alpha and beta coming in, and basically you see this potential term has got a constant height and then a modulation by beta. Very straightforward. And of course what happens to the rays depends on these constants. You either get oscillations or you get, like in terms of the pendulum, you get the pendulum either doing this when it's got enough energy or going backwards and forwards. So I don't want to go over the details of this material because it's fairly straightforward, and I have other things I'd like to say, but you know, it comes out of the machinery very straightforwardly. In the wave theory, we write down this covariant wave operator, absolutely standard, plug in, and we get a differential equation. Now for the amplitude, we can separate variables in x and y. And if you look at this is Mathieu's equation, as you might have expected. And if you take, of course, the WKB limit of this, you're back to the previous equation. This is the typical potential here, and one can now discuss its properties. You put in general solution by Floche or Bloch, and you can then pick up the Bragg condition, or Bragg conditions, and in the end you're led to look at the optical band structure using Hill determinants. Well, all of this is fairly standard. The point I'm making is it comes very quickly from going through this formula. Now, what about the full Maxwell's equations? Well, these are Maxwell's equations written in the standard way, and if we translate them, we can write them out like this. Now, I'm using what's called two forms, but you think of this as a wedge product, if you like, or a cross product rather. It's almost the same. You define this thing, which some of you may recognize from the relativistic formulation of Maxwell's equations. You define this tensor here, G, and then these two equations just boil down to saying that D of this is 0 and D of G is that. So these are the most fundamental equations in physics apart from those of general relativity, and these will work in any coordinate system. But of course, we need to close the system. We must relate F to G by constitutive relations, and here are the ones that we've used. So in our situation, we have a uniaxial system. I think that's the right terminology. Anyhow, we have these two perpendicular eigenvalues equal for the permittivity and permeability, and we can basically get these tensors coming in here, and they give us the relationship between the two tensors F and G. At the WKB level, of course, we just get two metrics depending on polarization, and that's really the extraordinary in the end. It depends on this whether B is or E is orthogonal. And again, I think this bit of optics is probably familiar to people, but it just drops out of this formulation. Now, we can use our machinery very easily. How do we use it? Well, we have a two form. In other words, we can actually write these f's in terms of these gadgets I called lambda. And I now just have to take the d. Well, I know what d of lambda is. It satisfies this nice condition that d of it is the wedge product of two others. And in this way, I can reduce the equations very simply, and I get back to this kind of equation here, which is giving me basically another generalized Latour equation. Now, of course, I could do this for other groups and other situations. The reason it's efficient is, of course, that it wasn't invented for one purpose or one group. It's just a universal way of solving these things for any choice of group. And it's very much the sort of thing that one does all the time in relativity. I'm afraid some typos have crept into this set of overheads. But for example, that should be lambda j wedge lambda. There should be a lowercase lambda and a wedge there. Okay, so let's conclude what we did. We claim to have revealed the underlying symmetry group of these chiral pneumatics and shown that we can think of the configuration as living on this group manifold. We've looked at the rays, integrated the ray equations. In fact, we justified the ray approximation by separation of variables. We looked at the resulting, by applying Floquet theories of band structure, and then we justified the approximations from Maxwell's equations. Okay, so that's an example of the use of standard methods from relativity, and I showed you earlier an overhead of the background radiation, and I said, well, people are calculating what would happen if our universe were actually described by this. They use the same methods. Now I want to go on to part two, and part two is a little different vein, more qualitative, and I want to relate two things. So these guys, this is Charlie Misner and this is Finkelstein, and in the 1950s they invented something called a gravitational kink. And what I want to say is that gravitational kinks, which are a highly theoretical concept, in other words, we probably don't believe that we could ever encounter a gravitational kink in nature, but they are closely related to this topological, to topological defects in pneumatics. And this gives a kind of different insight into solving some of the problems of that arise in the treatment of these things. And I'm going to discuss in particular droplets. So what's a gravitational kink? Well, I'm going to go back to square one and say what's a Lorentz metric. Well, the curve metric, I've explained locally, it's just a way of measuring lengths in three orthogonal directions. You can diagonalize that metric. And the main point is that the length in all three directions is positive. But if we have a space-time metric, one of those directions should be thought of as a time. And so one of them is going to have a negative eigenvalue for the metric. Now, in the mathematical classification of possible Lorentz metrics, so just to rub that thing in, perhaps I emphasize what I'm saying. The Euclidean metric is, of course, just a flat Euclidean metric is that, but of course, what we deal with in relativity in three dimensions is that metric. So that's the negative direction. Now, you can get from here to here in a very easy way. Let me just put a same symbol there. Now, you see the difference between these two is twice dt squared. So what that means is that if I have a positive definite metric on some space, I can find a Lorentzian metric by taking the metric I've got. Now imagine ordinary flat physical space and subtracting off twice a unit direction. Well, this is actually a bit bigger than what I want to subtract off. And, oh gosh, there should be a 2 here. Yeah, I want to cancel one of these, and I'm sorry, it should be a 2. And that will give me a Lorentz metric. Now, you can do the converse. Every Lorentz metric can be obtained by that kind of shenanigans. Well, actually, this is okay if I make alpha equals, I should have made alpha equals pi over 2. I think that's probably what I had in mind here. So if I choose alpha to be 45, for example, then this will be 2, and then I will be able to flip the side. So what's the geometry going on here? It's very simple. I've got some direction here, and then what I want to do is construct a light cone. And if that's 45 degrees, that's my light cone. So if I choose alpha to be pi over 2, I've got a light cone now. And that's basically what relativity is about. So when you classify possible Lorentz metrics, you say, well, I've got a manifold. I can always put a positive definite metric on it. And then actually to give a Lorentz metric, I have to give a direction field. It's not canonical, but it's qualitatively correct. So you capture some of the topology of a Lorentz metric by giving a direction field. Now, there's such a notion as time orientation, and an issue might be, can I tell past from future? If I can tell past from future, I can put an arrow here, and then I don't have a direction field so much as a vector field. So the issue of time orientability depends on whether I've got a vector field. Now, of course, in liquid crystals, that's to do with, do you have defects, as you probably know, which have a winding number of 1/2 or half fractional winding number or integer winding number. Okay. So my strategy is going to be, if you give me a configuration of the director field, I can make you a Lorentz metric. So that Lorentz metric will have certain properties, and they ought to translate into properties that we know about. Now, these two people, Misner and Finkelstein, were interested in the following problem, what they described as tumbling light cones. By the way, is this visible to the people here on this side? Okay, so their idea was there's something funny happening near black holes. So I can imagine something like this happening. The light cone's tumbling, and then maybe over here they could actually be tumbling in this direction. Okay? So I capture the idea of tumbling light cones. And so they wanted to characterize how that could happen, and they suggested, this is in the very early days of understanding conserved topological quantum numbers, we're talking 56, 57, they defined what they thought was a topological quantum number for general relativity. Well, it turns out that wasn't quite right, but the basic idea was to count how many times this light cone would tumble over. But actually that's also the same as closely related to kink number for the associated vector field. You see, because what we're really saying is that let's get another piece of chalk. I want to count. Okay, so what I've said is you can really think about this in terms of just a direction field, say pointing out like that, and then the direction field can move down and move down like that. And the number of times it changes is closely related to the kink number. Now mathematically you can do this as follows. You're interested in a surface, which I have called here sigma, which is the boundary of some region. And on big sigma, I can introduce a kink number, and the way I do it basically is to do the following. So I can describe it mathematically as follows. The surface has a normal And that normal then gives me what's called a section of the bundle of unit vectors over the surface, a surface in a four-dimensional space of unit vectors over. This is sigma. And the kink gives me something else. So that's n. I'm sorry, the light cone gives me something else. So what I actually get in this big bundle, this is sigma, and this is all vectors. So a graph, if you like, I get two graphs, one of which is nu, and the other of which is n. And generically, they will intersect in a certain number of points, and that is the kink number associated with the surface. And now the point is that if to have a regular metric without defects, well, you need a regular direction field. The regular direction field should not vanish anywhere. If it's to be non-vanishing, the topological condition for that is that the Euler characteristic of the domain, the Euler number, is equal, in fact, to the amount of kinking on the boundary. Now, of course, if we just talked about planar domains, then this kink is just the standard winding number that's familiar if you have a director field in the plane and you count the number of times the director field rotates as you move around a circle. If there are defects, of course, this relationship will no longer be true, and you'll count the number of defects by the extent to which it's not true. Okay. Well, you can then try to calculate this kink number and observe the tumbling light curves. I think I'm coming quite close to the end, so I think I'll have to go a bit faster through this. Just make a side remark. Of course, you could do the same thing with block walls. You have again a vector field which is related to magnetization. Okay, so how can you use this and how has it been used? So I want to talk about liquid crystal droplets now. Now, in a very naive model, you could demand that the angle between the normal of this is now the normal of the droplet. So my D is the droplet, if you like, and the director field, both of which are unit vectors, make a constant angle. If the free energy functional penalizes deviation from this angle. And so you look for surfaces for which that angle is constant with respect to a given direction field. Normally, you might think of the uniform isotropic phase, the direction field is vertical. And basically, if you put this in here, you're getting this formula here, because this is giving you the angle. Now, let's suppose this angle is scaled so that it's 45 degrees. You don't have to suppose this, but this is... so actually, this is telling you something about this surface. Now, we can translate that into the following. The normal is the gradient of a function s which defines our surface. The surface is s equals constant. And this combination is just the Lorentz metric inverted. So this equation is telling you that the gradient of s with respect to this Lorentz metric is 0. But that's telling you it's a wave surface or a null hypersurface. So finding null hypersurfaces on which the gradient is light-like is equivalent to solving this droplet equation. So what I'm basically saying is that the droplet, so here is the droplet, should be tangent to the light cone of our metric in order to have constant angle. There's a simpler way of thinking about this, a more homely illustration. If the coordinate is vertical, then the equation you get, of course, is just what's called the iconal equation. And that's what you have with a sand pile. You know, the thing about a sand pile, its job in life is to have slope fixed all over the surface. But of course, if you think of the vertical as time, this is the image of a focusing wavefront. So there's a one-to-one correspondence between the focusing of the wavefronts and the structure of sand piles. And sand piles are, of course, a manifestation of this boundary condition. So they can do a lot of interesting things. Here are some examples. I think I won't go through this, but if somebody asks me, there's also a relationship to domains in ferromagnets. But okay, so now if we want to find out what kind of droplets we can have, we just have to solve this equation. Now, it's well known to people who study general relativity as the Hamilton-Jacobi equation. It gives null geodesics. So, but another way is just the iconal one. So the easiest one to find is the spiral wave surface, which I've written out the formulae, but the spiral wave surface is just the involute of a circle. That is to say, you think of a circle, think of the tangents, and as you move around, you sweep out a spiral wave surface. Okay, so that kind of trivially solves the droplet equation, the boundary conditions in this case. For the helical phase, you can also find the shape of droplets, and you just substitute in. And the point about the Hamilton-Jacobi equation is you try to separate variables in an additive fashion, and if you push it through, you find that f of z comes up. Perhaps not surprisingly, it solves this quadrantal pendulum equation, and this surface is a ruled surface. It has horizontal straight lines, and also it has this constant slope. So one can describe it pretty much straightforwardly. So let me conclude the second part. What I've done in the second part is to associate with every director field, unit vector field, a Lorentzian metric, and in particular every pneumatic configuration has such a associated metric. And I've shown that the boundaries, for example, of droplets in an isotropic exterior correspond to null hypersurfaces. These surfaces have been studied quite a bit recently by some geometers under the name of constant slope surfaces, not, I think, realizing what their interpretation is. Now, that's more or less all I've got to say. I'll just conclude by saying this doesn't exhaust, as I indicated earlier, the things you can do in this vein. I alluded to the talk that Randy Camion gave. You can now pass to smectics, which of course is a different story altogether. If you believe that smectics, the basic order parameter, is a surface with constant separation, then you'll look at these surfaces of constant separation, and what you will do is you will say that they're given by a function w, and that function should satisfy the iconal equation, which just says that the gradient from surface to surface is unit length. Now this is, of course, just the wave equation in one extra dimension. So what Camion is doing is passing from 3 to 4 dimensions, introducing an artificial time, and in that way he's able to discuss the qualitative behavior of pneumatics. And for example, it's well known that in some circumstances you get these focal conics, which are given by beautiful surfaces, the surfaces of Dupin. You can lift those up to an extra dimension. It's purely a fictitious dimension given by the problem, but not a time dimension. Then they become wave surfaces in 4 dimensions, invariant under the action of the Lorentz group, and he's made great use of that in showing how Lorentz transformations take you from one configuration of focal conics to another. So what I assert is that there are other potential applications of this train of ideas to liquid crystals and similar configurations. Okay, but I should stop at that point. Thank you for your attention.
So thank you very much indeed for that entertaining and informative talk. Do we have some questions?
Yeah, I mean, this problem of droplets has been of some interest recently, and actually even in the early days of liquid crystals, the one thing that was observed was that the droplets were not round, but obtained some sort of peculiar shape which
Right.
people couldn't sort of quite figure out, and they actually invented special, they called it configurational strength. But I mean, what I so usually when we think about the shapes of droplets, we usually say, well, we've got some surface angular dependent surface tension, and then we've got some elastic energy inside, and we have to balance these things. And I mean, is it the case that you can sort of circumvent this
Well,
rather
I think
difficult?
the model is a simple model, and it leaves out a lot of physics. So the model is that there are two phases which are governed by the bulk energy separately, so maybe an isotropic phase outside and an anisotropic phase inside. And then you adopt this idea that the thing the surface energy that you're referring to, which is directional, will simply have a large minimum, I mean a deep minimum, on a certain angle.
All right, so you've got kind of strong anchoring.
That would be strong
What
anchoring.
we call strong anchoring. But the elasticity, some complicated elasticity calculation would be taken account of by your inside, would be taken account
Well, I
of
guess
your-
there you see that's where you have to choose what the director field is. For the director field that you choose, I mean, if you just consider a very simple situation where you have just the director field in the vertical direction, and maybe completely isotropic outside, you say, well, that's stabilized for some reason, and then you would have this rather simple calculation. I'm not saying that the whole calculation is simple. I mean, in principle, of course, you would write down the most general free energy function you could, which would take into account these properties. What I am saying is this emerges as an approximation in the case that you use the constant angle. Actually, the angle doesn't have to be constant. I showed that you could choose the angle. In fact, that alpha that I chose could vary over the surface. The interpretation in terms of Lorentzian geometry would still be valid because it was reduced to this iconal equation. Yeah, I mean, one has to be obviously careful about the limitations of these simple geometric models, and I'm perfectly aware that corners can be cut this way. But they do give you an interesting insight into why two problems are the same and what can be done.
For the droplet problem, I think that one wishes to have a compact surface as a solution to this problem.
Yeah, well, now that will require compact null hypersurfaces, which is fine, because what I said initially was it's very difficult to get these configurations in the real world, because you need a lot of mass, a lot of energy, it's not clear they're allowed. But I didn't insist that the director was, for example, not roughly radially directed from some defect. And then if I'm 45 degrees to that, I could imagine getting a compact surface surrounding that defect.
I think the general mathematical problem would be to devise proper conditions in the director that would imply that the solution, that there are compact solutions.
Okay. Yeah, that would be interesting. Yeah. I mean, I should say from my point of view, what's interesting about that is if those occur in nature, that's something which we don't believe occurs in general relativity because it would be grossly acausal. So they are a phenomenon which you can simulate in the laboratory in this analog system, which we don't believe.
Crystals contradict causality.
Well, you see, yeah, it would this phony causality because you'd have the light rays going around in circles because of the compact nature of this null hypersurface. So you'd be able to go backwards in time and things of that sort. So that's some of the more speculative things which I've been thinking about. As I said, I didn't try to get that into this review, but it does offer you an insight into the kind of dynamics that might be possible in general relativity because it's natural to think about these surfaces.
Do you think any of the insights you've got, I mean, I'm talking about the first part of your talk, do you think any of the insights you've got in treating Maxwell's equations could be of any practical use in the business of actually cranking out solutions of Maxwell's equations in complicated geometries?
Oh, I'm sure, yes, yes. I mean, they're a very efficient way of, I mean, nowadays you put them on a computer, they do the algebra. I mean, another direction, when I gave this talk to the photonics lab a year and a half ago, maybe more, they mentioned it's still, you know, the blue phase is still a big challenge to people. And if you look back at those papers of Sethner and others, they're using the three-sphere, basically they're using SU2 rather than this model, simply enough. It's not difficult to solve the Maxwell's equations on a group manifold, which is SU2, by the same techniques. I think there the obstacle is you know, the model that they had, which is that you relieve the frustration with the three-sphere, is, so far as I understand it, there's no simple model that's actually managed to give you a description of the blue phase in physical three-space. But somehow, you know, it's clear that something like SU2 is involved. Yeah, I think these methods are, I mean, it's the quickest way of teaching electromagnetism if the class actually understands the theory. It's just two equations. Well, come.
Rush back to our.
People said the same thing about vector analysis once.
Yeah.
They didn't like it.
And tensor analysis.
Yeah.
Okay, well, let's thank Professor Gibbons.